We are on the topic of generalized measurements or POVMs. Uh, right, and so as uh, the last time I just gave an axiomatic definitions of POVM uh, in the sense that we can is any set, right? So POVM is a set of positive operators. So I'm not gonna like write down the definition from last time. Just a short summary. Right. So these are positive operators that sum to the identity, uh, and that is all that's required for POVM. So they are more general than projective measurements. And this is a big subject and big and practical subject because it's related to directly to what experimentalists actually measure in the lab. Right? So the first example that we gave uh, in one sense, okay, so the last example that I gave was that, well, you can make a convex combination of projective measurements, right, or projective measurement, aka measurements of observables, and for example, I can flip a coin, and if it's come up head, I measure z. So suppose this is a qubit system, right? And if the coin comes up tails, then I measure x. And because of the probabilities of the coin flipping of 1/2, these are my POVM elements. So this really just uh, mixtures or uh, convex combination of measurement of observable. And so in a sense, well, and for example, this probability, so all of the POVM elements now are not projectors. They are scaled down projectors. They're not like scale projector is not necessarily a projector, right? Because for projector, you have to square to itself. And so if you scale, then that's not true anymore. But here signify the maximum probabilities that you could obtain for any given any states of the system. And so it's a sort of I mentioned last time, this is sort of a trade-off here that is kind of like adding noise to your measurements. But also this, for example, in this example, this allows allow us to measure two observable that do not commute, and normally we wouldn't able to measure them together. Commuting observable. And also, well, so it's sort of it's allow noisy measurement. It's also allow you to describe. So this is what we haven't talked about yet. I just alluded to last time that it's allow you to describe measurement of your system that is done by making a projective measurement on a larger systems. And so this is sort of the things that happens in the lab or in real life all the time, right? So practically, strictly speaking, any quantum measurement is not a perfect like projective measurement, right? So they're all POVMs in one way or another. And so it's like a big subject. There's like a whole book that's been written on measurements. And you may ask like, okay, if my measurement is not projective measurements, well, how do they, like, what are the classifications of other kinds of measurements? And then you have like a bunch of things. It's like, okay, it's like the diagram of, all kind of measurements that people think are important enough that they name them. But we're not gonna get into that. But yeah, just want to mention that this is a subject that is very relevant to like practical experimental physics, especially AMO, atomic molecular optical physics. Yes. If you go to quantum optics, a lot of it will be about how to actually make quantum measurements. Yeah. Well, so this seems like a good thing, or at least interesting. This seems like a bad thing, but not all measurements are, well, how to say, well, being noisy is not, I guess, as for this example, by being noisy, it allows us to do something more than what we were able to do with projective measurements, right? Another example that we're not gonna discuss soon is, for example, you can do unambiguous state discrimination using POVM, and this is the task where, say, suppose that I have a block sphere and then I have states that are not orthogonal. Maybe psi and phi. So if the states are orthogonal, you can devise a measurement that distinguish them perfectly, right? But if you try to do that with states that are not orthogonal, you will confuse between them sometimes. But with POVM, actually, you can make you can design measurements that actually never confuse between the two states. And well, we talk about this along the line, maybe next month after I come back. It's the topic of distinguishability of quantum states. But in this example, the idea is simple, right? The idea is that I can make a measurement along this axis. And so whenever I get this outcome, I know that, I have to decide whether I talk about block sphere or the 3D or vector in 3 dimensions. Well, let's see. Yeah. If this is a block sphere, the idea is that I can make a measurement that is orthogonal to this state, for example. So if I get this outcome, I will know that the state is not psi, and I can also make another POVM element to be in this direction. Although this picture is not very accurate because okay, so maybe let me I guess finish talking about, like, repeating the same thing first. So if I get the outcome that corresponds to this orange vector, then I know that the state is never it's not the phi state to begin with. But of course, the problem here is that these two projectors, these two POVM elements, do not sum to the identity. And so actually it turns out that you can sort of make it a little bit noisy. so that, well, the first POVM element is proportional to the projector to states that is orthogonal to psi. The second PO element of course are scaled down projectors on states orthogonal to phi, and then you can define the last one to simply be this, so that it sums to one. It turns out when you do the calculation that you need this scaling constant to be of certain value, so that E3 is still a positive operator, for example. And so when you add that, now this outcome E3 would just give you no information whatsoever about the state. It just say it doesn't know. But at the end of the day, what this allows you to do is to distinguish between these two states without ever confusing them, for example. Yeah, so it's not just so making things noisy, I guess just another example beside this one, that making things noisy allow you to do something more. Okay. More example. Example 1. Example 2. You can do cross grainings of POVM. It will still be a POVM. And what I mean by cross graining is that I can group different outcomes together, right? For example, I can make a POVM out of, for example, this. And then it will still be a POVM. So for temp, this is exactly what we do with state verification, right? We just group them together into the past projector. Well, not projector anymore, but you know. So for general qubit POVMs, the POVM elements, well, what are the form of the general POVM elements for qubits, right? So for the qubits, we know that we already have a way to write all possible positive operators, right? So everything that's on the block sphere or within the block ball is a positive operator, right? It's a set of density operator, but we can also change the trace as well, unlike the state where the trace is fixed to be 1. And so I can write it like this. So there'll be a vector here and scalar here. So maybe to be more explicit, I can pull out the magnitude and then write it in the usual form. So this part will control the probabilities, the maximum probability, like this, noise, and this control the ranks. The rank here meaning the dimension of the support of the operator, right? Because if R is 1, then you are on the surface of the block sphere and your operator is rank 1, and if you go inside, your operator is rank 2. So what are the constraints of these vectors? Well, so for positivity, we know, right, that in like, yeah, so we know how to um, characterize positive operator in this case, right? So everything that go outside the block sphere is not a positive operator. It has negative eigenvalues. And so, of course, this has to be, well, I think, yeah, right. And well, because it's sum to all the E alpha must sum to the identity, so Q must sum to 1 as well. Whereas uh, the coefficients, these vectorial coefficients in front of the Pauli parts had to cancel, right? So the vectorial sum must be 0. Yeah. And so, for example, we can design a measurement for. So this is one is called the tri measurement, and okay, I don't remember. Let me look up how I define it in the problem set. So if I just look at the xy plane in the block sphere, this is x, then the vector of the tri measurement is just this symmetric, just form a symmetric kind of like triangle. So it's of course also sometimes called the Mercedes-Benz measurement. Of course, this measurement gives you no information about the z component of your state, right? Because everything is on the xy plane. If you want to measure, have a single POVM that give you the information of any state, you can do this tetrahedron measurements, which is basically a pyramid. See? Well, not a pyramid, but a tetrahedron, which I draw here. So it will be go down from C to the base. So then, okay, how to make it 3D. Something like this. But it's just a polygon that kind of like higher dimensional triangle that has like equal symmetric and all. I have equal surface area, something like that, right? And when I say that this POVMs give you the information about where your state is on the block sphere, no matter where they are. They will also call say that this POVM or this measurement is informationally complete and can be used for quantum tomography. And what it means is that, well, suppose that I have an unknown qubit state. So let's talk about quantum tomography a little bit. Unknown qubit density operators. And if you are only allow projective measurements, how many measurements would you need to determine this unknown qubit state? Any guess? So if you're not allowed to use POVM and just projective measurement. So is the question clear that I have some state? It doesn't have to be on the surface, right? It's just some rho, but I just don't know. So I just well, it's somewhere there, but we don't know. But we want to make a measurement so that when I gather enough statistics, I can determine or I can infer what rho is supposed to be. So if now I can only allow, if I can make projective measurements or spin observable in some directions, so how many directions do you think at minimum that we need to determine this? What is the dimension of rho? Uh, you can say the number here, right? For a qubit system, what it is. What is it? Mm-hmm. So that would be 3, right? This is it consistent with what you call the dimension of rho? uh, yeah. Anyone else? Yeah, yeah. I think it's just a reasonable guess because the block sphere is in 3D, right? But the block sphere is not the Hilbert space, right? The Hilbert space is 2-dimension, but it's 2 complex dimension. Uh, the expectation value of the whatever we get, like probability of expectation value of the spin observable are real number. Uh, so it basically asks how many real parameter you need to specify the density matrix. So, and the block vector has 3 variable, right? Well, geometrically it's just x, y, z. And it turns out, right, we already know that the coordinates of n, well, here, it doesn't have to be a unit vector, right? This coordinates is exactly the expectation value of probably x, y, and z. Yeah. And so we need all 3 of them. And so you can think of this as separate observable, or you can group all of them into just a single POVM that has 6 POVM elements, right? Because each measurement has 2 outcomes. But here, if you do the tetrahedron measurement, instead you only do POVM with 4 POVM elements. Well, which one is easier, I don't know. You should ask experimentalists, not me. Yeah, it's just theoretically, it just sound nicer, right? In some sense. It's like what? Sorry. Not really, right? Because well, I think geometrically, I think these are clearly different measurement, just because these are just measurement along the Cartesian axis. Yeah, so how you how you recover the state from the statistic will also be a little bit different using these two measurements. Yeah, but it's a yeah, it's a good problem to think about, I think, of like what is the how to relate the geometry of the data that you get to the geometry of the block sphere. Any questions at this point? Okay, there's a one more example that I have want to give. And by the way, these are in homework set 4. I think is problem 3. You find out how to extend the tri and the tetrahedron measurement to projective measurement in a larger Hilbert space. So last example, just because I want to give an example in the continuous variable setting, the infinite dimensional Hilbert space setting. It is basically simultaneously X and P measurement. So measuring position and momentum at the same time. In the quantum optics lingo, it's called heterodyne measurement. Although I'm not, I would not be able to give to tell you how to actually make this measurement in the lab. But you can read it up on like quantum physics textbook, like Valentine. Okay, so some people in the room already know about coherent states already, because we did it in quantum, the first quantum class. Yes. So coherent state alpha are the set of states, or there are infinitely many of them. There are a set of states that are labeled by the eigenvalues of the annihilation operator. And recall, well, I have to look up the constant. So recall that when we're thinking about harmonic oscillators, so let's see how can I optimize the use of the blackboard here. Let's make some space. Make a note over here. So when we were dealing, or if you sometime when you learn about harmonic oscillator, the first thing that people do is to well, to focus on just the physics of the problem and not the units, they would make the x and p operator dimensionless first. And this is how you would do it. This is p, I think is bar m omega. So in this way, the commutation relation is just I. There's no h bar anymore. And then the annihilation operators, right, which is the operator that takes you take you a step down. When you apply to number operators, number states, so eigenstates of the harmonic oscillator, it takes you one step down, and it is, I think it's plus, yeah. So it's a complex linear combination of x and p. And a dagger is just the complex conjugate of this, so it's x minus ip, right? And so x and p, well, so essentially this, if you can sort of measure this annihilation operator, although it's not really a thing, right? Because annihilation operator is not Hermitian, so it's not an observable. But in a sense, this definition kind of suggests that, well, maybe I can just cut to the chase. So it turns out that this annihilation operator has eigenvector and eigenvalues, even though you cannot do a spectral decomposition from it because it's not a Hermitian operator, it's not normal operator. But this kind of already encodes x as the like the real part of alpha, right? So like well, just so x here is an operator, but I just mean it contains some information about the value of this operator. If you can, in some sense, measure these eigenvalues or measure these coherent states, and it turns out that you can, because they form POVM elements. So if you subnormalize them to with the constant 1/pi, they actually sum, or in this case integrate to the identity operator. So you can use this subnormalized projector as your POVM element. Well, so what it means, so I haven't really tell you about what these alpha states are. So one example is that the ground state of the simple harmonic oscillator, right, is actually a coherent state, because, well, the alpha here is just 0. And it turns out that so what we know about this is a minimum uncertainty state. In which so I think for so maybe just so recall that for energy eigenstate, denoted by n of the simple harmonic oscillator, we have this uncertainty. Yeah. So you might remember, you might not remember, but it's okay. But the important the spatial property is that both of these components are also equal. So if I sort of visualize this as a cartoon on the phase space, well, the phase space is usually you would usually denote the axis, use x and p as the axis, right? But actually, you can use alpha and alpha star as the axis as well. But anyway, well, so we actually know that the wave function of the ground state of the harmonic oscillator is a Gaussian, right? With no node. But if I were to visualize the uncertainty, it's kind of like this. It's kind of like quantum fuzziness. Whereas if say I have if I have an eigenstate of x, so the position eigenstate, the uncertainty would be something more like this. It has infinite uncertainty in the p in momentum. Or if I have eigenstate of p, then it's something like this. And in between coherent state and eigenstates of x and p, well, you also have like so-called squeeze state. Just draw it here just to say that there's a middle ground between the two here. But it turns out that every coherent state alpha is just well, maybe this is not the best way to say it, but it's just the ground state that has been picked from the origin. For example, if I switch to alpha and alpha star here, coherent state that specified by the value. So let's say this point is beta in the complex plane. This coherent state beta is really just a Gaussian that has been the same Gaussian as the ground state of the harmonic oscillator that has been kicked to this point in the phase space. So it still retains its shape. In this case, it means that it still has minimum uncertainty, and the uncertainty in every direction is the same. So I draw it like this, but in fact, any two coherent states are never orthogonal because they are Gaussians, and Gaussians wave function is decays, but it never really decays to zero, right? Just go to zero at infinity. So for example, if I were to write this down, let me just check the to make sure there's 1/2. 2. Yeah. So any two coherent states, when you take inner product together, they're not orthogonal. So they're never orthogonal. The inner product decays as they become further and further away, but they're never zeros. But yeah, you can define a POVM that whose POVM elements are scaled down coherent state. And by making this POVM, you make it a little bit noisy by the 1 over pi here, right? But now you're sort of measure uh, measure x and p at the same time. Because x is a real part of alpha, p is an imaginary part of alpha. Okay, any questions, comment? Mm-hmm. It's nice limited by quantum mechanics, so you cannot improve your detector beyond this point because uh, yeah, if it's not POVM, then you're not gonna get positive probabilities out of it, and so it's forbidden to do better. Mm-hmm. Uh, so you mean the set 0 and 1 for a qubit? Why would you put noise there? Or you're thinking about some experimental imperfection? Yeah, you can. Sure. So can you say that again? So we can model this with. Yeah. But you may ask how, right? One way to do it. Okay. I have an example from summer school. So yeah, thanks for the question. Uh, uh, yeah, you can always do that. But I would say that to model experimental imperfection, you should look at the thing about what is the model for the experiment, because otherwise you can put the noise in like in any way that you want, right? But if you but if you don't care about experimental realization, then why would you put noise there, for example? Yeah. So yes, let's talk about, because by the from that comment, let's talk about the one Lyman model of measurement. Yeah. So one way to make a measurement, well, actually, the model that von Neumann came up with, I guess, in his quantum mechanics textbook, is well, it's something that we kind of try to think about before, of a quantum system. Now I kind of that we usually denote by S. Now I kind of want to denote it by Q because quantum, but whatever. And then we have a meter M. Although before, in previous class, we think of M as a qubit, but one Neumann think of M as actually a meter. So it has a position. So it has a position and momentum degree of freedom. And you can think of the position as like really like where the meter points to. Um, and so to accomplish to use this kind of system to distinguish, for example, the 0 and 1 state, what you can do is that you can try to find an interact. You can couple this observable, this for the z observable to the momentum of the meter. And what it will do is that this momentum will generate a kick depending on the value of the spin measurement here. So let me write it down, but I might get the sign wrong. So you need coupling this. So maybe there's some continuous variable, and then the policy and the momentum operator. I don't remember if the translation operator is supposed to be this, right? So there's supposed to be a minus sign, right? I think. Yeah, just because every unitary evolution has a minus sign, so I think it's just this. So if I act this, right? So this is a unitary operator generated by this interaction, and let's see. So this is a qubit state. Yeah, let's just change it to Q. And then we have a meter. Let's say meter is in the state or wave function phi. And so this meter will have so step by step. This meter will oh sorry, the system is in some superposition, right, of 0 and 1. Then this is what we want to know by observing the meter systems. So the reason that we use this interaction, right, is because if I, right, yeah, I guess it's fine either way, whether this is plus or minus. If I let this unitary act on the state of the qubit first, this z will turn into the eigenvalue. Okay. So let me write like this. P, sorry, it doesn't look like P that much. And well, what is this? So this is a unitary operator generated by the momentum. So it's a translation operator, right? That kick the system here, I guess, is to the right by length phi. So maybe I should put some Latin alphabet here, but oh god, now there's 2 phi. Okay, that's fine. This is minus to the ket, and yeah, I think it should be. Yeah, and so now what happens that we have a superposition of the meter state, right? If so, originally the phi here is maybe like a Gaussian, maybe like Gaussian, or like peak at 0, and then if the depending on the coefficient alpha and beta, right, you have probability alpha square or beta square for us to to detect the meter pointing over, like move over here or over here, right? And so now if we measure the meter, then we know the spin state that the outcome of the spin measurement. So one way to model a noisy version of this is to make the initial wave function really wide. Right? And so once the pre-measurement state is done, so you have this entangled state, now the two outcomes will have some overlap. And so by measuring the position of the meter, you get some information about the spin state, but not always. It's noisy and you could confuse the up and down state. For historical reason, this is called one Neumann measurement model. So far, so good. And of course, you can here we sort of think of, well, so before this, so without this outside of this measurement model, so everything that we have said before, we don't think about the time to make measurement, right? The duration of making a measurement. We just say, okay, this is, we are given a POVM projector, just boom, the measurement happens. Here, maybe you can have, well, this is basically the time parameter. But if you want to go beyond that, if you want to make measurements that are continuous in time, in sense that for this, there is a time to turn on the interaction between the quantum system and the meter, right? But at the end, we still say that I just make like a instantaneous measurement of the meter. But if you want to know about making a measurement that are continuous in time, you can read this book. So you can use like stochastic calculus to describe measurements that are extended or continuous in time. Yeah. Yeah, unless you tell us experiment, don't do that. Just make the time as short as possible so that we don't have to think about it. All right. Which time is left? Half an hour. Good. Okay. Yeah, so those are the example of POVMs. I think that's all that I want to say generally about POVM. Wait, does one Neumann has 2n or just one? Maybe two. Yeah, maybe there's a typo there. So now you're ready to do all the homework in all the problems in homework 4. So far, as I mentioned, POEM give you the statistics of measurement, but not the post-measurement state. So what would give you post-measurement states are called quantum operations. So a quantum operation, so without, you know, specify exactly what properties are yet, like mathematical properties. Well, so these are evolution that the most general possible evolution when your, how to say, when at the initial time your system is not correlated with any other system. And you can model this, for example, like you have your system in so let's now I think now we have to label everything kind of and be consistent about it. So yeah, let's use some convention kind of similar to that. So system labeled by Q. And instead of the meter, because we may not use it for measurement, I would call the author system an ancilla instead. So it's just something that you add in. So quantum operations are what happens when, well, you have your state in the system. It's just something that you bring in. Well, I guess it's really just an English word. It's just something to bring into support, whatever. Yeah. And yeah, this is a singular one. This for plural, you have actually different ways to spell the plural form of ancilla. Either ancillas. I guess the American way is just put s at the end, but I think the original way is like ancilli, LAE. But okay, so quantum operation. So what we're gonna the situation we're gonna describe here is that we have a system. We bring in the ancilla in some state sigma. Then we evolve them together under some unitary operations, some joint unitary operations. And then we measure this, measure out the ancilla at the end. But we sort of have seen from the quantum circuit diagram, right, that it really, well, I guess we'll see it in more detail. It doesn't really matter if we actually measure this or not, or just tracing out, because tracing out is this, it's like ignoring this ancilla is equal to tracing out, and that is in turn equal to making a measurement but not looking at the outcome here and just averaging over all the outcomes. So there's some measurements. This I would call is the measurement model of quantum operation. And a quantum operation is how to describe this part by operators on the system alone. So just to emphasize again, I guess I mentioned this when you are away, that yeah, it is crucial in the quantum operation formalism that initially the system and the ancilla are not, the state of the system and the ancilla are not correlated, so not entangled. Yeah. If you want to describe, well, yeah, let's not go there. I call this a measurement model because everything has been specified. The interaction with the ancilla has been specified explicitly by the unitary here. So down the line, so maybe like next week or so, I will talk about other approaches to quantum operations and now how they are equivalent. More specifically, we can give an mathematically like axiomatic characterization of what we call quantum operations, without referring to like ancilla and unitaries. Yeah, but here, so here I just say that this is representation of quantum operations in terms of using this model that we call measurement model here first. Here, which means bringing in ancilla, evolve, and measure out the ancilla. So, okay, how can we describe this? So, yeah, let's try to describe the final state, the transformation to final state of the system. So the transform one is just denoted by a prime here. Okay, so what is this? So you start by you start in density matrix rho, right? And then you bring in the density matrix of the ancilla. You evolve them, and this you add on both Q and A, right? And then you measure it, or do I want to trace out, or I want to measure? Yeah. So let's say that this measurement is described by, let's say, it's projective measurements. It turns out we don't have to go beyond this and use POVM. And that is true for the initial state of the ancilla as well. We can use pure state as well if we keep extending the Hilbert space of the ancilla, right? But yeah, let's make it simple. Then make this P just projective measurement with outcome labeled by alpha or lambda. Well, yeah, let's use alpha here. Projective measurements. So I make a measurement, and then I also trace out. Trace out the ancilla. Okay. So do I want the probability? No, not really. Oh, sorry. So this is the final state if the outcome of the projective measurement on the ancilla is alpha, right? The outcome, yeah, and actually, I think I have to divide it by, yes. Oh God. Yeah, now we have to decide what's the most efficient notation here. Subscript Q. Then I don't need prime anymore. If I now I want to denote that is the post measurement state given outcome alpha, then I just put alpha here. But now I have to divide by the probability of getting the outcome alpha as well. Right. It's alpha. Yeah, so that's how you can write it. If you want to simplify a bit more, I can, because of cyclicity of the trace, I can bring the projector here to here, right? It's important, right, that this projector is on the ancilla only, because this trace is only on the ancilla. And then since it's a projector, it's combined into itself, it's square into itself. But if we ignore the measurement outcomes, we must average over all the outcomes here. So the final row now, yeah, is so I would just average or all the outcome, right, weighted by the probabilities. And so the probability cancel out. Okay. And now I can bring the sum inside the trace. Right. And what is this? Well, it's just a projective measurements, right? So this is just the identity. Is there anything that I can simplify? Yeah, that's the most we can do here at this point. So these are the post measurement states in this measurement model. Now we want to kind of group together all the operators in the ancilla system so that and write it in such a way that we only have operators. We only define operators in the that acts on the quantum system, the Q system. And let's see. Yeah, maybe I want to do that first. Yeah, do it in the same order. Yeah, so the case of, getting an outcome alpha. Should I start here or there? Okay. So let's also decompose these projectors into rank 1 projectors on some orthonormal basis. Right. Maybe lambda or something. Yeah, do it the usual way that we did. So J here is the label for the degeneracy, right? So if you do that, yeah, now you can do this. So we can start from here, right? The partial trace, I have this. And what the partial trace does here, well, I can turn, because of the trace, I can turn the outer product into an inner product. Put the slide the move the cat here. Well, actually, no more trace. Right. Mm-hmm. Well, and I think to proceed further, I should perform an eigen decomposition of this as well. So let's see that, let's say that this is lambda. I already used J there, I haven't used K. Some basis, but of well, not some basis, this is the eigenbasis of the density operator, right, of the ancilla. So now if I do that, I can write this guy like this. So let's split the lambda equally. Okay. Then E rho lambda K EKU dagger F alpha J. And now I define this to be okay, it's fine. Let's see. Oh, sorry, there must be a sum. Yeah, let's see if I want to put this K anywhere. Let's see. Yeah, that's fine. We must leave it like that. So I can define this to be uh, 3 indices. Yeah, that's 3 indices. Too bad. Alpha JK, and this one is just the Hermitian conjugate. The crucial point here, right, is that these are operators that acts on the system only. So U, the unitary U's, are acting on both systems. But now you take the partial inner product on both sides, so it's gonna take partial matrix elements of U in the ancilla Hilbert space. And so what is left is an operator on the Q, the system Q. And these, or rather A and not A dagger, are called Krauss operator. For here, it's corresponding to outcome alpha. So notice that if our projective measurements are rank 1, is rank 1, and if the state of the ancilla is a pure state, then we wouldn't have this sum jk, right? So there will be no label jk, and this would just be a single cross operator for the outcome alpha here. And well, this is usually so. So this there, so what we have been calculating, right, is the result of the transformation under this measurement model. And so usually this is, yeah, generally you think of this as a map from density operator to density operator. And here, since I use A for cross operator, I can use calligraphic A for the quantum operation when the outcome is alpha. So this thing rho is the input, right? You input the state, of the system, and you get out another state of the system. So without having without looking at the result, so again, the second case there, if I ignore the outcomes, then the total quantum operations, yeah, maybe just make a note here. This is just be summing over all quantum operation for the outcome alpha, then divided by the probability. Mm-hmm. Well, what is the probability here? Right. Let's do it over there. Better. The probability of getting an outcome alpha would just be the trace. This. And so if I write it out, right, mm-hmm. Yeah, all the sum has to be there. But then because of the cyclicity of the trace, I can move this A to the right side. And well, what is this? So for any operator, any linear operator A, the combination A dagger A is a positive operator. Right? And so when you sum them up, they are also positive operators. So this is nothing but P over M element corresponding to the outcome alpha. And so because of this, actually we know the constraint. Well, we can prove it, right? So does the sum of all these E alpha really the identity, right? So let's just calculate it. Okay. So alpha jk, right? Alpha jk. Well, what is this? So this is defined over there, right? That is lambda k EKU dagger F alpha j F alpha j U EK. So the only thing that depends on j here is in the middle, right? So if I move the sum over j over here, I will get the projector onto the outcome alpha. So now I get rid of one of the sum. Projector alpha. There's no trace there. Or should I? Let's see. It's the matrix element. I kind of want to move the P around. Yeah, actually, yeah, better way to do it, because I just want to get rid of this, right? And well, what is the transformation here? So actually, before I sum over alpha, so since these F alpha j are just elements of orthonormal basis, well, so when, let's see, can I do that? So I want to argue that the unitary will map orthonormal basis to orthonormal basis also. So now it's kind of weird because the U is acts on both the quantum system and the ancilla. Let's see. I think it's work, but maybe we can look at this again next time. Let's say, let's suppose that it works. Here, I would just, well, the alpha, that be only sum over k now. This is 1, and since the lambda k is the eigenvalues of the density operator of sigma, right, in its eigenbasis, this must sum to 1 as well, but now the operator disappear. Yeah, so I guess I can sort of do this, except that what I have left would be like an identity on the sorry, on the system itself is Q, not A. Okay, so it should be these E alpha should define the POM elements. And let me check the logic here, and I will come back to you next time because we already it's already known. So next week, yeah, the only normal classes, just Tuesday and Thursday. Maybe คำถาม